All right, so in this video, we're going to look a little bit at just exploring conics, exploring polar graphs just in general. Conics are in another video, but just exploring polar curves in general, kind of understanding how they work and what happens when you modify the polar graph a little bit. So we're going to start out with some circles that are nice and easy. Circles can just be represented by constants, and if you change the constant, you get bigger or smaller circles. Now, you can shift the circles off the origin a little bit by using a trig function. And so that's going to put the center halfway across the diameter. So our polar graph is going to look like this. And of course, if I make this coefficient larger, then I get a circle that is also shifted off the origin, but now by half of this coefficient. I can change the orientation by making this a sine curve. So instead of being on the right, it's now above the center of the axis. And I can shift it around to the other side by making it negative. So now it's below the x-axis, and I can do the same thing for cosine. I can have it on the left side of the axis by making that coefficient negative. So this is some information that we can use about these polar graphs. We can also, if we wanted to, have both sine and cosine functions. And that will actually tilt the graph a little bit. So for instance, if I have 4 cosine and 4 sine, I get a circle that's actually shifted off the origin like so. The actual center and the length of the diameter here is going to depend on these exact values of these coefficients, but you can, in theory, have both sine and cosine in your polar graph. There's nothing about this that requires that you have only the one. Now, the limacon and the cardioid are actually closely related to each other, so I want to explore that next. And so this is an example of a limacon with the inner loop. The relationship between the limacon and the cardioid is that when these two coefficients are different from each other, you're going to get a limacon, and when they're the same as each other, then you're going to get a cardioid. So if I make this a 1 cosine and a constant of 1, then I get a cardioid. If, on the other hand, I make either the coefficient of cosine larger or the coefficient of the constant value larger, then I get a limacon. Now, when the constant is larger, I get a limacon with no inner loop. When I make the coefficient of the cosine larger, then I get a limacon with an inner loop. And that's all the relationship is. Essentially the cardioid is a kind of limacon. It's just that it pinches off, and it's the transition between no loop and a loop. And again, we can change the orientation by changing from sine to cosine. And we can change which side of the axis it plots on by changing that sign, the SIGN sign, in between our two constants. Now, more interesting, if we can get more interesting polar graphs, is when we actually change the multiplier of theta. So one way that we can look at these graphs is if we have, let's actually make this a little smaller so we can see the whole thing. One way that we just have a single theta, but we have quite a few graphs that we have seen in our textbook where we have 2 thetas or 3 thetas. And so we can explore those. If I put a 2 here, I get a rose with 4 petals on it. And as long as I stick with even numbers, then I will get twice as many petals as I have multipliers of my theta. So when I had a 2 theta, I had 4 petals. If I have 4 theta, I have 8 petals. And if I make this 6 theta, I have 12 petals, and so on and so forth. If I don't have an even number, however, if I have an odd number, then I only get exactly the number of petals that I have multiplied by theta. So here I've got 3 petals. I can turn this into 5 petals or 7 petals and so on. So the multiplier of theta is going to affect the number of petals that I have, but it's also going to depend on whether that multiplier is even or odd for the exact number of petals I'm going to end up with. And this multiplier here just determines the length of the graph, the sort of maximum distance from the origin. So if I make this coefficient out here a 2, then the petals will be smaller. And if I make the coefficient larger, then the petals will be longer. Now, another thing that you can do is instead of using a whole number multiplier, you could divide theta by something. And then you get all kinds of interesting behaviors, but we're going to have to make theta larger so that we can actually see the whole graph. Here, I'm going to make it much larger because I want to experiment with lots of different values. So there'll be some repetition of this curve going all the way up to 50, but that's fine. It'll allow me to adjust this divisor and still get most of the graph. So you can see that if you divide theta by 2, you get this very interesting, nicely symmetric shape, which looks kind of fun. If I divide it by 3, I get what essentially looks like a limacon with an inner loop, which is kind of interesting. And if I divide it by 4, then I get something that looks similar to our divide by 2 example, but a little bit more complicated. And I can keep experimenting like this to see what happens. And you do get something that looks quite similar. In the odd examples, you get this shape that looks sort of like a limacon with the inner loop, but with this outer curve around it. And each time that you keep dividing, you get, again, a similar shape, but more nested. So again, this was our divide by 2 case, and then we got this outer one with our divide by 4 case. And now we have, again, this another embedded, more complicated behavior with our divide by 6 case. And if we divide by 7, we get the odd version. Again, flip the orientation. But now, again, we have this thing that looks kind of like a limacon with an inner loop. We've got the next thing that we saw when we were looking at the 5 case. And now we have the bigger one where we're looking at the 7 case. So again, you can adjust these. If you're using whole numbers, you'll get these very predefined shapes like this. But if you're using like decimals, then you can get all sorts of chaotic behaviors from your graphs. But I enjoy looking at some of these graphs just to kind of play with the idea of using them as a basis for art or design, in addition to just thinking about the effects that our coefficient changes are going to have on our graphs, so that we can, see our polar curves and we can kind of understand how they work together. Now, the last thing that we can look at for these kind of graphs is going to be, and again, you can add sines and cosines to them in different terms in order to make the graphs even more complicated. The last thing that I wanted to do an example of is a spiral. This is sometimes referred to as an exponential spiral. And the more that you adjust the theta, for instance, you can rescale it so that you can see it actually takes longer to spiral out. If we do something like this, it'll take a little bit longer. But essentially, when r is equal to theta, you get this spiraling behavior. And you can see that it starts at the origin and it spirals outward. You can also have a truly exponential spiral with like e to the minus value or e to the theta. And then you'll get, again, instead of having a fixed distance between spirals, you'll get a exponentially changing distance. But the theta by itself, without the sine or the cosine, is how you get this spiraling behavior.